Okay, I want you to imagine something. What if we could build a world not from the top down, but literally from the atom up? I'm talking about a world where tiny, microscopic machines patrol our bodies, repairing us cell by cell. Now, this sounds like something straight out of a movie, right? But it's not just a fantasy. It's the grand vision of nanotechnology. So today, we're going to dive into this incredible field. We'll separate that futuristic promise from what's actually happening in science right now and figure out the principles we'll need to navigate it all.
And it really all starts with this vision, one that feels totally sci-fi. This right here is the idea of a medical nanorobot. So what are we looking at? Well, these are theoretical machines built molecule by molecule, atom by atom. The idea is that we could put them into our bloodstream to monitor, repair, and protect our bodies on a scale we can't even imagine. It's just a breathtaking concept, isn't it? An army of tiny doctors inside of you working 24/7?
So what could this tiny army actually do? I mean, the possibilities are just astounding. We're talking about hunting down and destroying individual cancer cells, repairing damaged tissue, clearing out dangerous blood clots, basically waging a microscopic war on viruses and bacteria. But here's what's really a game changer. This is a shift from just curing disease to enabling constant preventative maintenance for our bodies. It's a whole new way of thinking about health.
And this is where it all leads, to the most audacious claim of them all. Think about it. If these nanorobots could continuously repair all the damage of aging at the cellular level, fighting off disease, fixing our DNA, basically keeping us in a state of perfect health, well, some futurists believe they could make biological immortality a real thing. I mean, just let that sink in. It's a staggering thought, and it just goes to show you the sheer scale of ambition we're talking about here.
All right. I know what you're thinking. This all sounds amazing, right? But it also sounds, well, a little like science fiction. Is this stuff centuries away, or is any of this happening now? That's the key question, right? We need to ground ourselves in reality.
So let's make that jump from the sci-fi dream to the actual science. Because look, while we don't have those autonomous, self-replicating nanobots patrolling our bloodstreams yet, the foundational work, the really important stuff, is happening in labs all over the world right now.
And this slide really lays it out perfectly. The vision versus the reality. The big dream, of course, is those autonomous medical nanorobots. But the practical reality, where the science is actually making huge strides today, is in something called nanotechnology-enabled biosensors. You can think of these as the first crucial step. They're basically the eyes and ears that any future nanorobot would absolutely need to do its job.
So what is a biosensor anyway? Well, to put it simply, it's a device that can detect a very specific biological thing, like a virus or a certain protein or a toxin. And when it finds it, it transforms that interaction into a signal we can actually measure, an electrical signal, a flash of light, something like that. It's really the bridge between the biological world inside our bodies and the electronic world we can read.
Okay, I know this looks super complicated, but it shows us something absolutely incredible. This is what's called designer nanomedicine. These aren't just simple little particles. A better way to think of them is like tiny programmable delivery drones. You can see all the different parts. There's a cargo section to hold the medicine, a protective shell, and then this outer layer with functionalization, which is just a fancy way of saying it has a built-in GPS system to help it find a very specific target, like one particular cancer cell. This is targeted, it's complex, and it's happening right now.
So why is nano such a huge deal for these biosensors? Well, it all comes down to the weird and wonderful properties that materials have at this incredibly tiny scale. I mean, we're talking about things like a massive surface-to-volume ratio and super high electrical conductivity. A material like graphene, which is just a single layer of carbon atoms, is the perfect example. It's a total wonder material for sensing because these unique properties let it detect the tiniest changes with incredible speed and sensitivity.
And here are some real-world examples that show you exactly where we are today. What you're seeing here are things like light-seeking nanorobots, which is a pretty basic but functional version of the kind of engine we'd need for those future medical bots. And then you have these complex diagnostic tools being developed. So are we at the final destination? No, not yet. But it's pretty clear the journey has already started.
But whenever you have this much power and potential, you absolutely have to ask some pretty serious questions. It's true for any powerful new technology, right? From nuclear power to AI. So how do we harness all the incredible benefits of nanotechnology while also managing the very real potential risks?
And that really is a central concern. There's this famous quote from a 2003 paper that says, "Ethical reflections lag behind this fast-developing science."
And you see this pattern again and again with new tech. Why does it happen? Well, the science just moves so fast in the lab. But for the rest of us, the societal implications, they don't feel real until the technology is practically at our doorstep. And by that point, it can be really hard to steer the ship.
But here's a really interesting thought. Does this mean we have to start the ethical discussion completely from scratch? Does nanotechnology present such brand new problems that we have nothing to guide us? Or can we maybe look to the past to help us navigate the future?
Well, it turns out the argument is that we don't have to start from scratch. In fact, a lot of the so-called nano-ethical questions are really just new versions of old problems we've already wrestled with for years in fields like biotechnology and genetics.
And this table just makes that point so clearly. Take the fear of runaway, self-replicating nanosystems. Sounds terrifying, right? But it's a very similar conversation to the one we've had about the uncontrolled spread of genetically modified crops. What about the toxicity of these new nanoparticles? Well, we have a long, painful history with toxic materials like asbestos to learn from. Human enhancement? We've been debating genetic enhancement for decades. And the invasion of privacy from nanosensors? That's just the next chapter in our ongoing struggle with digital surveillance. See the pattern?
Okay, so if the problems aren't totally brand new, that suggests we might already have the tools to think about them. So let's look at a framework, a way to navigate our nano future responsibly. It turns out bioethicists have already developed a really powerful toolkit of principles we can use. There are four main ones. First, you've got beneficence, which just asks, does it actually do good? Does it promote well-being? Then there's non-maleficence, which is kind of like the Hippocratic Oath. First, do no harm. You have to avoid inflicting harm. Third is autonomy, which is all about respecting a person's right to make their own choices. And finally, and this one's huge, is justice. Are the benefits and the risks spread out fairly? Who gets to use this stuff?
But here's the most important part. This is a balancing act. No single principle wins every time. In fact, they're often in tension with each other. I mean, think about it. A life-saving treatment is great for beneficence. It does good. But if it has risky side effects, it runs up against non-maleficence, do no harm. So it's always this conscious act of balancing these competing ideas. And this image just illustrates that balancing act perfectly. Every single breakthrough has potential consequences that we have to weigh. So you see the positive outcomes, that's beneficence, the good it can do. But then you have the negative possibilities. High costs? That's a question of justice. The risk of damaging cells? That's about non-maleficence. You see? Every step forward means we have to carefully weigh both sides.
So, let's wrap this all up. What are the big takeaways here? First, nanotechnology is this wild mix of a futuristic vision and a very real, fast-moving science. Second, the applications that are happening right now are mostly focused on things like nanobiosensors and targeted medicine. Third, the ethical challenges are for sure significant, but they aren't totally new. We can learn from our past. And finally, and this is key, we already have established ethical principles to help guide us toward responsible development.
And that really leaves us with one final critical question. Because look, the advance of this technology, it feels inevitable. So the real challenge for us, the question we all have to answer, isn't if we'll use nanotechnology, it's how. How will we choose to shape our future with it? It's about deciding what kind of world we want to build, one tiny atom at a time.